Somebody on the data team shipped a churn model that predicted a customer had a 140% chance of leaving. Another row came back at minus 30%. The model was not broken in any way the code could detect. It ran, it trained, the error went down, and it printed numbers that cannot exist. Here is how you get there, and it is the most reasonable path in the world. You have a column of labels that are ones and zeros. This customer left, this one stayed. You already know how to fit a straight line through numbers. So you fit a straight line through the ones and zeros. Rate times tenure, plus a coefficient on support tickets, plus a base. Minimize the squared distance between your line and the labels. It converges. It even correlates with reality. And it will hand you 1.4 for a customer who is very likely to leave, because a straight line does not know it has been asked for a probability. You can shrug and clip it. Clamp anything above 1 down to 1, anything below 0 up to 0, and move on with your afternoon. That instinct is worth interrogating, because clipping destroys the only thing you actually wanted. A probability is not a score. A probability is a promise about long-run frequency. Of the 1,000 customers I labeled 0.7, roughly 700 should actually leave. Once you clip, every customer above the ceiling collapses into the same value, and you can no longer tell the merely likely from the nearly certain. And the moment you want to make a decision, is it worth spending $40 of retention credit on this person, you need the real number, because the decision compares $40 against the probability times the lifetime value. A clipped score cannot do that arithmetic. So the output has to live between 0 and 1 by construction, not by force. That is the first repair, and it is a small one. Take the straight line you already fit and pass its output through a squashing function. Big positive input goes to almost 1, big negative input goes to almost 0, and 0 goes to exactly 1/2. The standard choice is the logistic function, 1 over 1 plus e to the minus z, where z is your old linear combination. Its shape is the S you have seen 1,000 times, and Pierre Verhulst introduced it in the 1830s to model how populations saturate rather than growing forever. Now, what does that squashing actually mean, because it looks like a hack? It is not. Invert it, and something interpretable falls out. If p is the probability, then z equals the log of p over 1 minus p. That fraction, probability of the event divided by the probability of no event, is the odds. 3 to 1 odds is a fraction of 3. So z is the logarithm of the odds, and your linear model was never predicting the probability. It was predicting the log odds. Sit with that for a second, because it makes the whole model readable. A coefficient of 0.6 on a feature does not mean the probability rises by 0.6. It means that a 1-unit increase in that feature adds 0.6 to the log odds, which multiplies the odds by e to the 0.6, about 1.8. That feature nearly doubles the odds. Every time. Regardless of where you started. That constant multiplier on the odds structure is the actual assumption you are making, and it is a strong one, worth knowing you have made it. So the outputs are honest now. They sit strictly between 0 and 1. Keep the loss you already had, keep minimizing squared error against the labels, and you have logistic regression, in the version almost everybody invents on their first attempt. It is broken. In 2 different ways, and the second one is worse. Start with the one you can feel. Imagine a customer who genuinely left, so the label is 1, and your model is extremely confident they would stay. Its linear output z is minus 6, so the squashed probability is about 0.0025. Maximally wrong, maximally confident. That is precisely the mistake you most want to correct, and the update you get is almost nothing. The reason is the chain rule. To change your weights you need the slope of the loss with respect to z, and squared error contributes a factor of the squashing function's own slope. That slope is largest in the middle 1/4, at z equals 0, and it collapses towards 0 out in the tails. At z equals minus 6 it is about 0.0025. So your gradient is multiplied by roughly 1/100th of the value it would have had in the middle. Divide it out and you get the number that matters. The confidently wrong example produces an update about 100 times weaker than a merely uncertain one. Read that as behavior rather than arithmetic. The model learns fastest where it is already unsure, and it barely learns at all where it is catastrophically overconfident. It has exactly the wrong priorities. Saturate a few weights early in training, and those units go quiet and stay quiet for thousands of steps. The second failure is quieter and more structural. Squared error against a squashed output is not a convex function of the weights. The bowl-shaped landscape that made linear regression safe, one bottom, guaranteed reachable, is gone. You get a surface with flats and dips, and the pleasant guarantee that gradient descent finds the best answer no longer holds for a model with 2 parameters and 100 rows of data. You have imported the pathology of deep learning into a problem that did not need it. Both failures come from the same source. Squared error was never the right way to score a probability. So define what a right way would look like, and derive the loss instead of guessing it. You want a penalty that depends on how much probability you assign to what actually happened. If the truth is 1 and you said 0.9, you should pay a little. If you said 0.5, you should pay more. If you said 0.01, you should pay a lot, and if you said exactly 0, you claimed the observed event was impossible, and you should pay everything, because no amount of evidence can rescue a claim of impossibility. There is exactly one natural function with that shape, the negative logarithm. Minus log of 0.9 is about 0.11. Minus log of 1/2 is 0.69. Minus log of 0.01 is 4.6. And minus log of 0 is infinite. The penalty grows without bound precisely as your confidence in the wrong answer approaches certainty. That is cross-entropy, also called log loss. For a single example, it is minus log of the probability you assign to the true outcome. Averaged over your data, it is one number that measures how surprised your model is by reality, surprise measured in the same units Claude Shannon used in 1948 when he defined information. A loss of 0.69 means you are contributing nothing beyond a coin flip. That is the number to beat before you talk about accuracy. Compare the two losses on the same catastrophe and the difference stops being philosophical. True label 1, prediction 0.01. Squared error says the penalty is 0.98 bounded, unremarkable, barely worse than being wrong at 0.1. Cross entropy says 4.6. Squared error's worst possible penalty for a probability is 1. Cross entropy has no worst case, which is the entire point. It takes confident errors seriously. Now the payoff, and it is genuinely elegant. Work out the gradient of cross entropy with respect to z, and the squashing function's troublesome slope cancels out exactly. What survives is the predicted probability minus the label. That is the whole thing. Times the feature, for a given weight. Look at the consequences. The update is proportional to your error, with nothing damping it. The confidently wrong example from before, at probability 0.0025 with a label of 1, produces an error of nearly 1, the largest correction available, instead of the smallest. And the expression is the same shape as the gradient of linear regression, prediction minus target, times the input. 2 different models, 2 different losses, 1 identical update rule. Cross entropy is not merely better behaved than squared error here. It is the loss that makes the squashing function invisible to the optimizer. The cancellation is not a coincidence, and there is a deeper story underneath it. Ask what your model is claiming. Probabilistically, each label is a single coin flip whose bias is the probability your model produced. Write down the likelihood of your entire dataset under that claim, take its logarithm to turn the product into a sum, and negate it so that smaller is better. What you get is cross entropy, exactly, with nothing added. So cross entropy is the negative log likelihood of a coin flip model, and squared error is the negative log likelihood of a bell curve model. Neither is a rule of nature. Choosing a loss is choosing what kind of noise you believe your labels have. Squared error believes your zeros and ones are real valued measurements with symmetric Gaussian error, which is a strange thing to believe about a customer who either cancelled or did not. Which is the moment the story turns, because the honest version of this model does not converge. Suppose your features happen to separate the two classes perfectly, a single tenure threshold below which everybody left and above which everybody stayed. Real data does this more often than you would like, especially with many features and few rows, and especially when a feature has quietly leaked the answer. Maximum likelihood now has no finite solution. Every time you scale the weights up, the probabilities push further towards 0 and 1, and the loss gets strictly smaller. There is no bottom. Your coefficients run off towards infinity, and the only thing that stops them is the iteration limit. The model looks spectacular in training and its confidence is entirely manufactured. The fix is to stop asking for pure maximum likelihood. Add a penalty on the size of the weights, a small multiple of their squared magnitude, and the objective regains a finite minimum, because unbounded confidence now costs something. Which is why every logistic regression in every serious library ships with regularization switched on by default, and why turning it off is a decision rather than a simplification. 2 more things that bite in production, both downstream of the same idea. First, the loss is undefined at exactly 0 and 1, so never compute log of a probability you produced by squashing. Keep the raw log odds and use the fused implementation your framework provides, the one whose name mentions logits rather than probabilities, because it evaluates the loss in a rearranged form that never takes the logarithm of a rounded to zero float. That single substitution is the difference between a stable training run and a sudden not a number at step 9000. Second, the threshold is not part of the model. Cross-entropy trains the probability, 1/2 as a cutoff is a separate, later decision, and usually the wrong one. If only 2% of your customers churn, a model that maximizes accuracy should predict stays for everybody and be right 98% of the time. That model is worthless and its log loss is bad, which is the argument for the loss. It is a proper scoring rule, meaning it is minimized only when your stated probabilities match the real frequencies. Optimize cross-entropy to get calibrated numbers, then pick the threshold from the cost of each kind of mistake. If you are wondering how far a model's 0.7 can drift from a real 70%, plot the answer against your held-out data before you trust a single decision made from it. The honest caveats are worth naming. Convexity holds for this model and dies the moment you stack layers, so the guarantee is a property of linear log odds, not of cross-entropy. And because your labels are hard zeros and ones while reality is noisy, minimizing log loss pushes the model to be more certain than the world justifies, which is why large classifiers soften their targets slightly rather than demanding absolute confidence. And the reason any of this earns 15 minutes, this small model is the final layer of nearly everything. Swap the two outcome squashing for its many outcome cousin, where each score is exponentiated and divided by the total, and cross-entropy generalizes unchanged to 1,000 classes. A language model predicting the next token out of 100,000 possibilities is doing exactly this, once per token, on features a transformer learned for it. Its famous perplexity score is nothing more than e raised to the cross-entropy. Every classifier you have ever trained ends in this shape. So carry 3 things. Squashing the output was the easy repair, and keeping squared error afterwards was the real bug. It learns most slowly exactly where it is most wrong. Then, cross-entropy is not an alternative penalty someone preferred, it is the negative log likelihood of the coin flip you already claimed your model was, and its gradient collapses to prediction minus label because of that. And the part that matters most, it trains a calibrated probability, not a decision, so the threshold and the cost of being wrong remain your job and never the model's. As for the churn model with the 140% customer, the rewrite was 30 lines. Same features, log odds output, log loss with the fused numerically stable implementation, a small weight penalty because 2 features nearly separated the classes. The predictions came back between 0 and 1, and more importantly the ones labeled 0.7 churned about 70% of the time. The retention team stopped asking who was going to leave. They started asking who was worth $40, which is a question the model can finally answer, because it now returns a probability instead of a score that merely resembled one.